Welcome to this lecture on animal behavior. Today, we are going to explore one of the most fascinating phenomena in the natural world, instinct. Imagine buying a brand new smartphone. Even before you connect it to Wi-Fi or download a single app, it already knows how to search for a network and ring when someone calls. In the animal kingdom, instinct works exactly like this pre-installed software. Let us dive in and see how nature programs survival right into the brain. Now that we have our smartphone analogy, let us look at a real-world example. When a baby sea turtle hatches on a dark beach, it does not attend a class to learn how to swim. It immediately turns toward the brightest horizon, usually the moon reflecting off the water, and scrambles toward the waves. This behavior is completely unlearned. The turtle is born with the instructions already written into its brain. Instincts ensure animals can perform critical tasks from the very first second they enter the world, without needing a teacher. Building on that incredible sea turtle example, let us define this scientifically. In ethology, which is the study of animal behavior, an instinct is an innate, highly stereotyped pattern of behavior. When we say a behavior is innate, we mean it is genetically hardwired. It is inherited directly from the animal's parents through DNA, exactly like eye color, beak shape, or fur texture. It requires absolutely no prior learning or experience. The animal simply knows what to do the moment the situation arises. So, how exactly does the brain know when to trigger these hardwired behaviors? It works like a biological lock and key. First, there is a specific environmental cue called a sign stimulus, or a releaser. When the animal's nervous system detects this specific key, it activates an innate releasing mechanism in the brain. This mechanism is the lock. Once unlocked, the animal performs a fixed action pattern. This is a rigid sequence of unlearned acts that, once initiated, is usually carried to completion, even if the original stimulus is suddenly removed. You might be wondering, why do animals rely on these rigid, robotic instincts instead of just learning as they grow, like humans do? The answer comes down to survival. Learning takes time, consumes massive amounts of energy, and involves making dangerous mistakes. In the wild, failing to recognize a predator means instant death. There is no second chance. For example, a newborn foal must instinctively know how to stand up and nurse within minutes of birth, or it will be left behind by the herd and perish. Instincts guarantee a perfect first-time response. Now that we understand what an instinct is and why it matters, let us look at how it works mathematically. Konrad Lorenz proposed a threshold model to explain this. The formula is R equals I sub s times m sub I minus t. Conceptually, an animal builds up internal motivation that pushes against a mental threshold, while an external stimulus pulls on it. In this equation, R is the magnitude of the instinctual response. I sub s is the intensity of the external sign stimulus. M sub I is the internal motivation, like hunger or hormones. Finally, T is the innate threshold resistance. The behavior only happens if the combined force of the stimulus and motivation overcomes this threshold. Let us see this formula in action with a classic experiment. During mating season, a male stickleback fish will instinctively attack any rival male. The sign stimulus is the red underbelly of the rival. Suppose the red color intensity is 8 units. The defending male's internal motivation, driven by testosterone, is 3 units. The genetic threshold to trigger an attack is 15 units. We want to know if he will attack. We start with our formula. We substitute 8 for the stimulus, 3 for the motivation, and 15 for the threshold. Multiplying 8 by 3 gives 24. Subtracting 15 leaves us with a final response magnitude of 9 units. Because 9 is greater than 0, the attack instinct is successfully triggered. That stickleback example shows a normal instinctual release. But what happens if we trick the system? This brings us to a fascinating phenomenon called a supernormal stimulus. A female greylag goose has a powerful instinct to roll any displaced egg back into her nest using her beak. The sign stimulus is simply the smooth, rounded shape of the egg. But what if a mischievous scientist places a giant, smooth volleyball near the nest? The volleyball has an exaggerated size, creating a massive artificial stimulus. Let us calculate what happens in the goose's brain when she has to choose between her real egg and the volleyball. Before we look at the volleyball, let us calculate the goose's baseline reaction to her normal egg. We are given that her internal motivation to incubate is 4 units, and her threshold for egg rolling is 10 units. The normal egg provides a natural stimulus intensity of 3 units. We plug these into our threshold formula. We multiply the stimulus of 3 by the motivation of 4, which gives us 12. Then we subtract the threshold of 10. This results in a final response magnitude of 2 units. The instinct is successfully triggered, but as we can see, the biological drive is relatively mild. Now, let us run the exact same calculation for the giant volleyball. The goose's internal motivation remains at 4 units, and her genetic threshold is still 10 units. However, the artificially high stimulus intensity of the giant volleyball is 12 units. We multiply this massive stimulus of 12 by her internal motivation of 4, giving us a total drive of 48. We then subtract the threshold of 10. This results in a massive final response magnitude of 38 units. The math clearly shows us how powerfully the artificial object stimulates her nervous system compared to the real egg. Let us compare those two results. The response magnitude for the volleyball is 38, which is vastly larger than the response of 2 for her actual egg. Physically, this means the goose's nervous system is completely hijacked by the exaggerated features of the volleyball. She will instinctively abandon her real egg and exhaust herself trying to roll the giant volleyball into her nest. This perfectly illustrates a crucial point. Instincts are blind, mechanical responses to specific cues. They are not conscious, logical decisions. The animal is simply obeying the biological mathematics we just calculated. To visualize everything we have discussed, let us look at Konrad Lorenz's famous psychohydraulic model. Imagine a water reservoir representing the animal's internal motivation, constantly filling up. The tap at the top is adding action-specific energy. At the bottom, there is a spring-loaded valve representing the innate threshold. Notice the weight pulling on the valve. This represents the external sign stimulus. When the combination of the water pressure inside and the weight pulling outside overcomes the spring, the valve opens. The water pours out into a slanted trough with multiple holes, representing the release of the fixed action pattern. It is a perfect mechanical metaphor for instinct. We have covered a lot of ground today, so let us summarize the key takeaways. First, an instinct is a powerful, genetically pre-programmed behavior that requires no prior learning, ensuring immediate survival. Second, these behaviors operate on a lock and key mechanism, where a specific sign stimulus unlocks an innate releasing mechanism to produce a fixed action pattern. Finally, while this system is incredibly efficient, it is also highly mechanical and blind, meaning it can be easily hijacked by supernormal stimuli. You now have a solid mathematical and biological understanding of how animal instincts work.